Good afternoon. The topic for today's lesson is graphs of rational functions, and also looking at asymptotic behavior of those functions. That's one example of a rational function. We have a polynomial in the numerator and a polynomial in the denominator, and two asymptotes, x equals 0 and y equals 4x squared. That means that if y is the quotient of p in x over q in x, and p in x and q in x are both polynomials, then the graph will be the graph of a rational function. You already learned about hyperbolas, truncus. They are simple examples of rational functions, and you've learned about vertical and horizontal asymptotes. So, hyperbola 1 over x minus 1, x equals 1 is a vertical asymptote, whatever makes 0 of the denominator. Truncus, if I have quadratic over quadratic, I can split it into two fractions, 2 plus 1 over x squared. So that's your truncus translated 2 units up. We have a vertical asymptote x equals 0 and the horizontal asymptote y equals 2. Now there are other types of asymptotes which we call oblique asymptotes. So if I have cubic over quadratic and I divide everything by x squared, this expression simplifies to x plus 1 plus 1x squared. So now x equals 0 will be a vertical asymptote, but y equals x plus 1 is an oblique asymptote, like a linear asymptote here. Why is it happening? If x becomes very, very big, 1 over x is very small, so y will be approaching x plus 1 on both sides. But we can also have a parabolic or a curved asymptote, like we have cubic over linear, y equals 4x squared plus 8 over x. Again, x equals 0 is a vertical asymptote, but y equals 4x squared is a curved parabolic asymptote. So we see our graph approaches the parabola here, approaches the vertical asymptote in the middle, similarly approaches the parabola there and the vertical asymptote here. So we can have oblique asymptotes and parabolic asymptotes or curved asymptotes. So let's have a look at the first example. Sketch the graph of y equals x squared plus 1 over x. Let's divide first. So write it in the form y equals x plus 1 on x, because from this form we can tell the asymptotes. So vertical asymptotes x equals 0 and oblique asymptote y equals x. There is no x-intercept, we can't make x or y equal to 0, it would be undefined. So now stationary points, we differentiate. If we differentiate this form, it's 1 minus 1 on x squared. If we put it on one line, it's x squared minus 1 on x squared. For this fraction to be 0, the top is 0, which is 0 when x is 1 or x equals minus 1. So we have two stationary points. The second derivative of this expression is 2x2 minus 3, which is 2 over x cubed. The second derivative is at x equal 1 equals 2, which is positive, so that's a local minimum. When x equals minus 1, 2 over minus 1 is minus 2. The second derivative is negative, so this point minus 1 minus 2 is a local maximum. Points of inflection, the second derivative is never 0, so there is no point of inflection. Concavity, when x is positive, the second derivative is positive, so the graph is concave up. When x is negative, the second derivative is negative, so the graph is concave down. So we have vertical asymptote, x is 0, y equals x is on oblique asymptote, local minimum, local maximum, so the graph approaches asymptotes and passes through those 2 points. Now we change plus to minus and we do the same thing, divide first x minus 1 on x. So we have 2 asymptotes, x equals 0 vertical and y equals x oblique. We have x-intercepts, is when x is 1 and minus 1, it is the x-intercepts. There is no y-intercepts because x cannot be equal to 0. Stationary points, so we differentiate this form 1 plus 1 over x squared. That's always positive, it's never 0. There is no solution, so no stationary points. Points of inflection, again differentiate. It's minus 2 over x cubed. Again, the second derivative is never 0, so it's no points of inflection. But we can look at concavity. When x is positive, the second derivative is negative, so it's concave down. When x is negative, the second derivative is positive, so the graph is concave up. So 2 x-intercepts, no stationary points, 2 asymptotes, and we put all that together. Vertical asymptote, oblique, x-intercepts, the graph is concave up here and concave down, approaching the asymptotes. Example 3, y equals x cubed plus 16 over x. Same thing, we divide first to get x squared plus 16 over x. So we have 2 asymptotes, vertical x equals 0 and parabolic asymptote y equals x squared. X-intercept, we use this form to solve, equals 0 when x cubed is negative 16. So x is cubed root of negative 16, and that's the approximate value. Again, no y-intercept, x cannot be 0. It is a vertical asymptote. Stationary points, differentiate here 2x minus 16 on x squared, put back on one line, and equal to 0. So x cubed equals 8 and x equals 2. There is one stationary point. The second derivative, so if we differentiate this, 2 plus 32 over x cubed, when x equals 2, the second derivative is positive. Therefore, this point 2 and 12, if we substitute 2 back into the equation, is a local minimum. Points of inflection, differentiated the second derivative, so now we solve it for 0 by putting it on a common denominator. X cubed is minus 16, so x is cubed root of minus 16, which is the same as our x-intercept. So point of inflection at the x-intercept. Concavity, to the left of this point the graph is concave down, to the right of this point it's concave up. So we draw our parabolic asymptote. We know we have x-intercept, which also is the inflection point, so it would be concave up here, concave down, and the graph is concave up there all the way with the local minimum at this point. Now that's another example from your textbook, x squared plus 4 over x squared minus 5x plus 4. So if we factorize the denominator, we get x equals 1 and x equals 4 are the vertical asymptotes. If we divide, we get the horizontal asymptote x equals 1. What's interesting here is that the graph approaches the horizontal asymptote to the left and to the right, but it actually crosses it at this point, and it can happen with rational functions, and there was an example like that on an exam. So we might have a horizontal asymptote for a very big values of x or very small, but at some point in the middle, the graph could still cross the asymptote. So please enter that onto your calculator, and you can do calculus for this function to see that we have just a turning point here and look at concavity. So that's a more complicated function. Most likely, this graph would be with a calculator. Another example which relates a bit to methods, which is optimization. So we have the capacity of a baked bean is 250 cubic centimeters or 250 mils. And we want to find the radius and height of the can with the smallest total surface area. So the surface area is 2 pi RH plus 2 pi R squared, that's cylinder. But we know the volume is 250, so we can make H the subject here and substitute into the area and simplify. So this is a rational function. We differentiate this function and solve for 0 to get the exact value of the radius. Then if we differentiate again here, we get the second derivative, and when r is positive, the second derivative is positive. So as expected, the area, the total surface area at this point will be minimum. And that's how it would look on your graph. There is a good example in your textbook. So if you go to 6G chapter and resources, there is the video example 30 showing another example of a rational function. So to sketch a graph of a rational function, we need to determine the asymptotes, axis-intercepts, if exist stationary points, again, might be there or not, points of inflection, and concavity. So please attempt this exercise, try those questions by hand, and 17 with CAS. And ask for any help if unsure.